Hello, welcome back. Chemistry is fun when we understand it. In this next video of my series on titrations, we're going to calculate the pH once we have passed the equivalence point. That means any of these points in this region marked with E. I also want to remind you that I have a couple of videos where I go over the general aspects of titrations. For now, just remember that you usually have a sample for which you want to know the concentration. For that, you reacted with a standard solution of known concentration that you call the titrant. And then you follow how the properties of your solution, for example the pH, change as you're adding more titrant. And with that you end up with something that looks like this that we call the titration curve. For the purposes of a numerical example, we're going to be looking at this one point that is next to the equivalence point. Every single point that comes after are going to be solved in a very similar fashion. Now remember that titrations are reactions that go to completion, so the amounts and the composition of your flask change, so does the volume, because you're adding titrant to your initial sample. So here's a statement of the problem. I already mentioned that this is past the equivalence point, but let's just go and work it out from scratch. Remember that volumes and amounts change because you're adding a titrant. So work with moles, and at the very end, with the recalculated volume, you can readjust the concentrations. This equation is the most important part on these type of problems. Number of protons reacted is equal to the number of hydroxide ions reacted. With that, we have to calculate the amounts of each one of those species that are coming respectively from your acid and your titrant or base. Let's do the calculation for the protons in my acid sample. Remember, concentration times volume, that gives me the amount. I'm working with millimoles just for the ease of calculation. That corresponds to those of my acid. With this factor, I'm looking at how many units of protons are contained per unit of my acid, and I end up calculating the amounts of protons that are present in my sample. I'm going to do something similar to my base. Concentration times volume, amounts of sodium hydroxide, then the units of hydroxide ions per unit of sodium hydroxide. I end up with the amounts in millimoles of hydroxide ions. Now, you may be tempted to just use this particular equation, C1V1 equals C2V2, but beware that that's not always the case. This special equation tells you that you have to look at number of moles. That is related to the stoichiometry, and so if you set up your unit analysis correctly, you're always going to get the right answer. So please do unit analysis. Do not shy away from it. Unit analysis is your friend. It's always going to help you go in the right direction to get the right answer. That being said, remember, reactions go to completion. You have to calculate the corresponding amounts. We just did that. The next question is there a limiting reactant? Yes, there is. This one is the one that is in a smaller amount present for the reaction, so the sample is going to be my limiting reactant. With that, I can calculate the compositions and the amounts coming from the reaction, and for that I'm going to use a BARF table. Compositions and volumes are changing, so I can recalculate the concentrations of the relevant species. That will allow me to find the pH, and I'm going to do that with a RICE table. So a two-step process in this problem. The first one calculating amounts with a BARF table, the next one calculating concentrations with a RICE table as seem appropriate. Let's go with the first part. Since we're working with amounts corresponding to a BARF table, amounts before action, amounts reacted, amounts final. The question is, what action? The action of your two components reacting to give you a product. Filling up this table, I already calculated the amounts of each one of those species. I determined that my sample was the limiting reactant that get consumed all the way. I end up with 0 at the end of the reaction. The limiting reactant determines how many moles of my titrant are reacting, so how many are left, but also determines or limits the amount of product that can be formed. Now remember that at any point during this titration curve, the pH is given by the composition and the concentrations in this final row after the reaction in my BARF table. In terms of the composition, we can see that we have two species surviving. One of them is a strong base, the other one is going to be the conjugate base of my weak acid. We came from the equivalence point, so since we keep adding titrant, let's treat this problem as if you started with a weak base type of problem to which you're just adding some extra strong base to it. We're going to be using the value of Kb. We have a mixture of two bases. We're expecting to have a basic pH at the end, and then we can calculate the pOH using this relationship. So let's do it. We readjust the volume. Final volume is 50 milliliters. Then we can calculate the concentrations using the amounts from my BARF table and this recalculated volume for each one of the species that are important in this case, which are going to be my hydroxide ions and also the weak base. Now, with this one, changes for my reactants is minus X, for my products is plus X. At equilibrium, initial concentration minus X. For the acid, conjugate acid, is going to be X, but for my base or hydroxide ion, it's going to be initial concentration plus X. So this is very important because if we're thinking about this problem in terms of an equilibrium of my weak base, the fact that we're putting an excess of hydroxide ion is shifting my equilibrium to the left. That's immediately telling me that this one is going to stay mostly as this species, not reacting with water. So the number of hydroxide ions that are coming from this reaction and of the weak base are going to be minimal. So we're expecting that this value of X is much smaller than the value of the initial concentration of the hydroxide ions coming from my strong base. Let's solve this problem again the most general way. Let's not drop any values. Let's just do the calculations. So we set up the equilibrium expression for my Kb, products over reactants, the numerical value from the relationship Ka, Kb, and Kw. We end up with this numerical value, and then the expression, we substitute the equilibrium concentrations that we have from my Rice table. This expression is going to give me a quadratic equation that I can solve any way I want. We're going to get two roots. We take the one that is meaningful physically. In this case, it's going to be the positive root. And then to calculate the OH minus, according to my Rice table, is take the initial concentration, the excess titrant, plus X. But look at this. Initial concentration was 10 to the minus 2. This one is in the order of 10 to the minus 9. So this is much smaller. When I put them together, basically the concentration is the same of the initial concentration that I already had. So with that, I can calculate the value of POH. 14 minus POH is going to give me the pH. Now, is this result what we expected? Yes. Since we already have past the equivalence point, we have a mixture of two bases, one weak, one strong. And with that two bases, the pH will have to be larger than 7, and this is what we have. At least we know that we're going in the right direction. Now, for these two concentrations, the weak base and my strong base, they're on the same order of magnitude. This setup, it's always going to give you the right answer. And what we can effectively conclude is that in this mixture of weak base and strong base, the strong base is the one that imposes the final pH. Okay, I hope this is helpful. Let me know if you have any questions, and I'll see you in the next video.